Okay, kind of doing the same thing. Let's look at example 5, which is number 18 in the book, talking about diagonals. So again, if y'all wouldn't mind, let's pause it. Let's read number 18, kind of get a good idea of what they might be asking, and then hit play and we'll pick up right here. Okay, so we're taking a newer equation. This equation relates, we're looking at basically a box's diagonal, and then we have x, y, and z as being the dimensions, so length, width, and height. And this S represents just the diagonal of this box. Okay. First part A says that we want to assume that the x, y, and z are both functions, differentiable functions of time. So we're going to be taking the derivatives all with respect to dt. And we want to know, how does the diagonal relate to all the other ones? Okay. So pretty much that first problem is telling us that x, y, and z, all three are considered variables. Nothing's constant here. So ds dt is going to equal, in this process here, we have almost that chain rule. Okay, I've got a base to a power. So first of all, I just want to focus on the base to the power. So if I would normally bring the power down front, have my base, and then I would have to subtract 1 from the power, right? Okay, so I'm just going to leave the base the way it is, x squared plus y squared plus z squared. However, now because all my variables are in the base, I've got to multiply by the derivative of that base, which is 2x dx dt plus 2y dy dt, and then plus 2z dz dt. Okay, and I mean, if we wanted to, we can go through the whole process of cleaning it up. You notice how 1/2 out here in the front is going to be multiplied by all of these 2's inside of here. So if we wanted to, we can cancel all those 2's off and cancel that 1/2 away. And then since this is to the negative power, we could write all of these as x dx dt over x squared plus y squared plus z squared. If you want to write it to the 1/2 power or put it back under the radical, it's up to you. And then it would be then plus y dy dt over, again, the same thing, because we're distributing this front all the way through this parentheses. So again, this is just making it look pretty. It's up to you if you want to take it this far. Okay, so this would be finding the rate of change of the diagonal, assuming that all three dimensions are also changing, your length, your width, and your height. And that's what this first part is telling you what to do. Okay. Now part B. It says in part B is, how does the change in diagonal relate if x is held constant? So x is a constant variable. Well, starting out again, so the change in the diagonal, it's going to be, again, we need to focus on just the exponent part, so it's going to be 1/2 x squared plus y squared plus z squared to the negative 1/2. And now I have to go in here and take the derivative of the base. Well, this time they're telling us that x is constant, so when I take the derivative of x squared, it's just going to be 0, and then the 2y dy dt plus 2z dz dt. So to answer then the question of how it relates, it's basically going to be, see, the 1/2 is still going to cancel with those 2's right there. It's basically going to be just these two fractions right here in part A. So if you want me to just write them out just real quick, it'll be y dy dt over x squared plus y squared plus z squared to the 1/2, and then plus z dz dt over x squared plus y squared plus z squared to the 1/2. Okay, so moving right along, let's go to part C. Part C says, how are all the changes related if S is constant? So if, in other words, if the diagonal is constant, then how are the dimensions going to change? Well, going back into our equation, when it says S equals, then that means it's going to be 0 equals, and then x, y, and z are still variables, so it's still going to be then taking the 1/2, your base, to the negative 1/2 power, and then times the derivative of your base. So 2x dx dt plus 2y dy dt plus 2z dz dt. And cleaning it up, how about we write this? 0 is equal to, how about this? part A. And there you go. And you can use all this right side right there. Its only difference is it's going to be 0 equals all that. All right. Number 22 in the book. Okay, I went ahead and put up some information. Basically, the problem's giving to us is we basically have a box with dimensions x, y, and z. So I kind of drew that out here on the right side. And they gave us some information, the change in x with respect to time, the change in y, and the change in z. Okay, and they want us to all find some specific values. So first of all, in part A, we want to know is that how does the rate at which the box's volume is changing with respect to the dimensions. Okay, so the volume of a box obviously is just side times side times side. So if we want to find the rate of change of the volume, we have dv dt, and again we're going to treat each of these variables as they're all variables. Both x, y, and z are. There's no constants in there. Well, how do you do it when you have a product of three things? Let's treat it almost like, let's pair it up. Let's do x and then we'll treat y, z together. So it's going to be first times the derivative of the second, I'll write it like this, times the derivative of the second plus the second times the derivative of the first. So I'll write it kind of like it's primed right there. Okay, now let's go and expand this out then a little bit more because we're going to have a product rule inside of the product rule. Okay, so first times the derivative of the second, and it's a product, so now inside of here we have first times the derivative of the second plus the second times the derivative of the first. And again, I'm writing these all as dy dt's, dz dt's because it's all with respect to time. Okay. So that's first times the derivative of the second, and the second times the derivative of the first. And moving on to the second term, then we're going to have yz times the derivative of x, which is dx dt. To be, it looks like 2, and then dimensions here, since volume, it would be, meters times meters times meters, so it would be meters cubed, and then per second. Okay, so there's the answer for part A. What I'm going to do is erase this part here that I just did for part A, leave all the other information up there, and let's go into part B. Okay, so in part B, what we're doing is we're analyzing the rate and change of the surface area of this box. And let's come up here to the formula and see if that makes sense to you. Do you see how I go 2xy and 2xz? So the surface area, you're really just looking at these sides. And I've got this side right here, which is x times y. You've got a front, and then you've got a back to it. This side right here, that's just y is z. You've got two of these. It's one on this side, and then one over here on this side. And then the xz, which represents the top and the bottom. That's why you always have then a total of 2 of each one of those. Okay. So to start this problem out, we're just going to be taking, the derivative of the surface area. So ds dt is going to equal, and then we're going to treat everything here just like they're all variables. So let's pull off the 2, and then we have x times y, so we have a product rule. First times the derivative of the second plus the second times the derivative of the first. Okay, and then plus, we have pull off the 2 there, and we have first times the derivative of the second plus the second times the derivative of the first. And one more time, let's pull the 2 off, and we have first times the derivative of the second plus the second times the derivative of the first. Okay, all we have to do is plug in our information. So it's going to be 2 times, we have x, which is 4, times dy dt, which is negative 2, plus y, which is 3, times dx dt, which is 1, plus 2, x, which is 4, dz dt, which is 1, and z, which is 2, dx dt is 1, and 2 times y, which is 3, dz dt is 1, and z, which is 2, times dy dt, which is negative 2. Okay, cleaning the rest of this up, and just kind of combining all the numbers together, and we'll get our answer. So ds dt, let's see, 2 times negative 8 plus 5 is negative 5, plus 2 times 6, plus 2 times, let's see, 3 minus 4 is negative 1. It looks like 12 minus 2 minus 10, so it looks like that ds dt comes out to 0. So there's absolutely no change in the surface area for these specific conditions. Very interesting. That can definitely happen. All right, let's wrap this one problem up. Let's go to part C. And in part C, we're just taking the derivative of the diagonal with respect to the dimensions x, y, and z. Definitely something we should recognize from our very last problem. So we can almost just copy and paste that derivative down here. So it's going to be 1/2 x squared plus y squared plus z squared to the negative 1/2, and then times the derivative of the base. So 2x dx dt plus 2y dy dt, and then plus 2z dz dt. And because we want to use the cleaned up form of this, I'm just going to take the 1/2 away in all those 2's. And I'm actually going to choose not to have to write this as individual fractions, because I only want to plug here for that first parentheses. Let's just plug it in once, since we're going to actually find values here. Okay, so again, all we have to do is just plug in what we have. So x squared, let me go ahead and do this. Go ahead and write 16 plus y squared plus z squared. Oops, let's write that as a 4. Okay, all of that to the negative 1/2 power. And then x, so 4 times its change, which is 1, plus y, which is 3 times its change, negative 2. And z is 2 times its change, which is 1. Okay, so combining all this together, we'll get a change in the diagonal to be, over here on the left, it looks like we're going to be having to take the square root, it looks like of 29, which is not going to be fun. If we look at the right, 4 minus 6 plus 2 is actually 0. So if all of that right there is 0, at least 0 times anything is 0. And that'll give us in the terms of meters per second. Okay, box that up, and we're ready for the next problem.